All right, hey everyone, morning and welcome back. So what I'd like to do today is continue our discussion of naive Bayes, and in particular, we describe how to use naive Bayes, a generative learning algorithm, to build a spam classifier that will almost work, right? And so today you see how Laplace smoothing is one other idea. You need to add to the naive Bayes algorithm we described on Monday to really make it work for, say, email spam classification or for text classification. And then we'll talk about a different version of naive Bayes that's even better than the one we've been discussing so far. Talk a little bit about advice for applying machine learning algorithms. So this will be useful to you as you get started on your CS229 class projects as well. This is a strategy for how to choose an algorithm and what to do first and what to do second. And then we'll start with intro to support vector machines. Okay. So to recap, the naive Bayes algorithm is a generative learning algorithm in which, given a piece of email or Twitter message or some piece of text, take a dictionary and put in zeros and ones depending on whether different words appear in a particular email. And so this becomes your feature representation for, say, an email that you're trying to classify as spam or not spam. So using the indicator function notation, I should use J. Xj, I've been trying to use a subscript J not consistently to denote the indexes and the features, and I to index and training examples. I'm noticing I'm not very consistent in that. But so Xj is whether or not the indicator for whether word J appears in an email. And so to build a generative model for this, we need to model these two terms, P of x given y and P of y. So Gaussian discrete analysis models these two terms with a Gaussian and a Bernoulli, respectively, and naive Bayes uses a different model. And with naive Bayes in particular, P of x given y is modeled as a product of the conditional probabilities of the individual features given the class label y. And so the parameters of the naive Bayes model are phi subscript y is the class prior. What's the chance that y is equal to 1 before you've seen any features? As well as phi subscript j given y equals 0, which is a chance of that word appearing in a non-spam, as well as phi subscript j given y equals 1, which is a chance of that word appearing in spam email. Okay? And so if you derive the maximum likelihood estimates, you will find that the maximum likelihood estimates of phi y is this. Right, just a fraction of training examples that was equal to spam. And the maximum likelihood estimates of this and this is just the indicator function notation way of writing. Look at all of your emails with label y equals 0 and count up in what fraction of them did this feature xj appear, did this word xj appear. Right? And then finally, at prediction time, let's see. Yeah. You will calculate P of y equals 1 given x. This is kind of according to Bayes' rule. Okay. All right. So it turns out this algorithm will almost work. And here's where it breaks down, which is so actually every year there are some CS229 students, some machine learning students who do a class project, and some of you will end up submitting this to an academic conference, right? Some of CS229 class projects get submitted, as conference papers pretty much every year. One of the top machine learning conferences is the conference NIPS. NIPS stands for Neural Information Processing Systems. Let's say that in your dictionary, you have 10,000 words in your dictionary. Let's say that the NIPS conference, the word NIPS corresponds to word number 6017, right? In your, in your 10,000 word dictionary. But up until now, presumably you've not had a lot of emails from your friends asking, hey, do you want to submit a paper to the NIPS conference or not? And so if you use your current set of emails to find these maximum likelihood estimates of parameters, you will probably estimate that probability of seeing this word, given that it's spam email, is probably 0, right? 0 over the number of examples that you've labeled as spam in your email. So if you train up this model using your personal email, probably none of the emails you've received for the last few months had the word NIPS in it, maybe. And so if you plug in this formula for the maximum likely estimate, the numerator is 0, and so your estimate of this probably is 0. And then similarly, this is also 0 over, the number of non-spam emails, I guess. Right, so that's what, it's just this formula, right? And statistically, it's just a bad idea to say that the chance of something is 0 just because you haven't seen it yet. And where this will cause the naive Bayes algorithm to break down is if you use these as estimates of the parameters. So this is your estimate parameter phi subscript 6017 given y equals 1. This is phi subscript 6017 given y equals 0, I guess. And if you ever calculate this probability, that is equal to a product from I equals 1 through n. Let's say you have 10,000 words. P of xi equals 1. P of xi given y, right? And so if you train your spam classifier on the email you've gotten up until today, and then after CS229, your project teammates start sending you emails saying, hey, we like the class project. Shall we consider submitting this class project to the NIPS conference? Right? NIPS conference deadline is usually in sort of May or June most years. So, finish your class project this December, work on it some more, right? January, February, March, April next year, and then maybe submit to the conference May or June of 2019. But if you start getting emails from your friends saying, let's submit our papers to the NIPS conference, then when you start to see the word NIPS in your email, maybe in March of next year, this product of probabilities will have a 0 in it, right? And so this thing that I've just circled will evaluate to 0, because you're multiplying a lot of numbers, one of which is 0. And in the same way, this is also 0, right? And this is also 0, because there'll be that one term in that product over there. And so what that means is if you train a spam classifier today, using all the data you have in your email inbox so far, and if tomorrow or 2 months from now, whatever, the first time you get an email from your teammates that has the word NIPS in it, your spam classifier will estimate this probability as 0 over 0 plus 0, okay? Now, apart from the divide by 0 error, it turns out that statistically it's just a bad idea, right, to estimate the probability of something as 0 just because you have not seen it once yet, right? So what I want to do is describe to you Laplace smoothing, which is a technique that helps address this problem, okay? And in order to motivate Laplace smoothing, let me use let me use a different example for now, right? Let's see. All right. So, several years ago, this is older data, but several years ago, so let me put aside Naive Bayes. I want to talk about Laplace moving, and I'll come back to apply Laplace moving to Naive Bayes. So several years ago, I was tracking the progress of the Stanford football team. This is a few years ago now. But that year, on 9/12, our football team played Wake Forest. And, actually, these were all the state games we played that year. Right, and we did not win that game. Then on 10/10, we played Oregon State, and we did not win that game. Played Arizona, we did not win that game. We played Caltech, we did not win that game. And the question is, these were all the away games, all the other state games we played that year. And so if you're the Stanford football team's biggest fan, you follow them to every single other state game and watch all these games. The question is, after this unfortunate streak, when you go on, this is actually a game on New Year's Eve, you follow them to their Oklahoma game, what's your estimate of their chance of their winning or losing? Right? Now, if you use maximum likelihood, so let's say this is the variable x, you would estimate the probability of their winning. Well, maximum likelihood is really count up the number of wins, right, and divide that by the number of wins plus the number of losses, right? And so in this case, you would estimate this as 0 divided by number of wins was 0, number of losses was 4, right, which is equal to 0, okay? That's kind of mean, right? They lost 4 games, but you say, no, the chance that they're winning is 0, absolute certainty. Right? And just statistically, this is not a good idea. And so with Laplace moving, what we're going to do is imagine that we saw the positive outcomes, the number of wins, just add 1 to the number of wins we actually saw, and also the number of losses, add 1, right? So if you actually saw 0 wins, pretend you saw 1, and you saw 4 losses, pretend you saw 1 more than you actually saw. And so Laplace moving, going to end up adding 1 to the numerator and adding 2 to the denominator. And so this ends up being 1/6, right? And that's actually a more reasonable, maybe it's a more reasonable estimate for the chance of the winning or losing the next game. And there's actually a certain set of circumstances under which there's an optimal estimate. So I didn't just make this out of thin air. But Laplace, sort of ancient but well-known, very influential mathematician, he was actually trying to estimate the chance of the sun rising the next day. And the reasoning was, well, we've seen the sun rise a lot of times, and so, but that doesn't mean we should be absolutely certain the sun will still rise tomorrow, right? And so his reasoning was, well, we've seen the sun rise 10,000 times, we can be really certain the sun will rise again tomorrow, but maybe not absolutely certain because maybe something will go wrong, or who knows what will happen in this galaxy. And so his reasoning was he derived the optimal way of estimating, really the chance the sun will rise tomorrow. And this is actually an optimal estimate under, I'll say the set of assumptions, we don't need to worry about it, but it turns out that we assume that you are Bayesian with a uniform Bayesian prior on the chance of the sun rising tomorrow. So if the chance of the sun rising tomorrow is uniformly distributed, in the unit interval, anywhere from 0 to 1, then after a set of observations of this coin toss of whether the sun rises, this is actually the Bayesian optimal estimate of the chance of the sun rising tomorrow. Okay? If you don't understand what I just said in the last 30 seconds, don't worry about it. It's taught in sort of Bayesian statistics, advanced Bayesian statistics classes. But mechanically, what you should do is take this formula and add 1 to the number of counts you actually saw for each of the possible outcomes. And more generally, if you're estimating probabilities for a k-way random variable, then you estimate the chance of x being I to be equal to So that's the maximum likelihood estimate. And for Laplace smoothing, you'd add 1 to the numerator and add k to the denominator. Okay? So for naive Bayes, the way this modifies your parameter estimates is this. I'm just going to copy over the formula from above. Right? So that's the maximum likelihood estimate. And with Laplace smoothing, you add 1 to the numerator and add 2 to the denominator. And this means that your estimates of these probabilities, they're never exactly 0 or exactly 1, which takes away that problem of the 0 over 0. Okay. And so if you implement this algorithm, it's not like a great span classifier, but it's not terrible either. And one nice thing about this algorithm is it's so simple, right? Estimating the parameters is just counting, can be done very efficiently, right? Just by counting, and then at classification time, it's just multiplying a bunch of probabilities together. So it's a very computation efficient algorithm. All right, any questions about this? Yeah. Oh, sorry, this is why. Oh, yes, thank you. Yes, thank you. Great. All right. Oh, by the way, I was actually following the Stanford football team that year, so, they lost. It's okay. I love a football team. They're doing much better now. This was a few years ago. All right. So in the example we've talked about so far, the features were binarily valued. And so actually, one quick generalization, when the features are multinomial value, then the generalization, actually here's one example. We talked about predicting housing prices, right? That was our very first motivating example. Let's say you have a classification problem instead, which is you're listing a house, you estimate what is the chance that this house will be sold within the next 30 days. So it's a classification problem. So if one of the features is the size of the house, x, right, then one way to turn the feature into a discrete feature would be to choose a few buckets. So if the size is less than 400 square feet versus 400 to 800 or 800 to 1200 or greater than 1200 square feet, then you can set the feature xi to one of 4 values, right? So this is how you discretize a continuous value feature to a discrete value feature. And if you want to apply naive Bayes to this problem, then probably of x given y, this is just same as before, product from I equals 1 through n p of xj given y, where now this can be a multinomial probability, right? Where if x now takes on one of 4 values, say, then this can be estimated as a multinomial probability. So instead of a Bernoulli distribution over 2 possible outcomes, this can be a probability mass function, probably over 4 possible outcomes if you discretize the size of a house into 4 values. And if you have a discretized variables, typical rule of thumb in machine learning, often we discretize variables into 10 values, into 10 buckets. That's just it often seems to work well enough. I drew 4 here, so I don't have to write out 10 buckets, but if you have a discretizing variables, for most people will start off with discretizing things into 10 values. Now, right, and so this is how you can apply naive Bayes to other problems as well, including classifying, for example, if a house is likely to be sold in the next 30 days. Okay. Now, there's a different variation on naive Bayes that I want to describe to you that is actually much better for the specific problem of text classification. And so our feature representation for X so far was the following, right? With a dictionary A aardvark by, you know, right? So let's say you get an email that's, you know, a very spammy email that's drugs, buy drugs now. Right. This is meant as an illustrative example. I'm not telling any of you to buy drugs. So if you have a dictionary of 10,000 words, then I guess let's say A is word 1, aardvark is word 2. Just to make this example concrete, let's say the word buy is word 800, drugs is the word 1600, and let's say now is the 6200th word in your 10,000 words in a sorted dictionary. Then the representation for X will be 0, 0, right, and then put a 1 there and a 1 there and a 1 there. Okay. Now, one interesting thing about naive Bayes is that it throws away the fact that the word drugs has appeared twice, right? So that's losing a little bit of information. And in this feature representation, each feature is either 0 or 1, right? And that's part of why it throws away the information that with the one word drugs appeared twice and maybe should be given more weight in your classifier. There's a different representation which is specific to text. And I think text data has a property that they can be very long or very short. You can have a 5-word email or a 1,000-word email. And somehow you're taking very short or very long emails and just mapping them to a feature vector that's always the same length. Here's a different representation for this email, which is for that email that says drugs, buy drugs now, we're going to represent it as a 4-dimensional feature vector. Right, and so this is going to be n-dimensional for an email of length n. So rather than a 10,000 dimensional feature vector, we now have a 4-dimensional feature vector, but now xj is an index from 1 to 10,000 instead of just being 0 or 1. Okay, and n is, and I guess n varies by training example. So ni is the length of email I. So if a longer email, this vector, the feature vector x will be longer. And if a shorter email, this feature vector will be shorter. Okay. So let's see. Just to give names to the algorithms we're going to develop, these are really very confusing, very horrible names, but this is what the community calls them. The model we've talked about so far is sometimes called the multivariate Bernoulli event model. So Bernoulli means coin tosses. So multivariate means there are 10,000 Bernoulli random variables in this model. Right? So it's a multivariate Bernoulli event model. And event comes from statistics, I guess. And the new representation we're going to talk about is called the multinomial event model. These two names frankly, these two names are quite confusing, but these are the names that I think, actually one of my friends, Andrew McCallum, as far as I know, wrote the paper that named these two algorithms, but I think these are the names we seem to use. And so with this new model, we're going to build a generative model. And because it's a generative model, we'll model P of x comma y, which can be factored as follows. And using the naive Bayes assumption, we're going to assume that P of x given y is product from I equals 1 through n, j equals 1 through n, of P of xj given y, and then times, P of y is that second term, right? Now, one of the reasons these two models were frankly actually very confusing to the machine learning community is because this is exactly the equation that you saw on Monday when we described naive Bayes for the first time. P of x given y is product of probabilities, right? So this equation looks cosmetically identical, but with this new model, the second model, the confusingly named multinomial event model, the definition of xj and the definition of n is very different, right? So instead of a product from 1 through 10,000, it's a product from 1 through the number of words in your email, and this is now instead a multinomial probability rather than a binary or Bernoulli probability, okay? And it turns out that, with this model, the parameters are, same as before, phi y is probably of y equals 1, and also the other parameter of this model, phi k, given y equals 0, is a chance of xj equals k given y equals 0, right? And just to make sure you understand the notation, see if this makes sense. So this probability is the chance of word blank being blank if label y equals 0. So what goes in those two blanks? Actually, what goes in the second blank? Let's see. Well, what? Yeah. Yes. Right? Yeah. So there's a chance of the third word in the email being the word drugs, so the chance of the second word in the email being buy or whatever. And one part of what we implicitly assume, maybe why this is tricky, is that we assume that this probability doesn't depend on j, right? That for every position in the email, for the chance of the first word being drugs, the same as chance of the second word being drugs, the same as the third word being drugs, which is why on the left-hand side, j doesn't actually appear on the left-hand side, right? Make sense? Any questions about this? And so the way you calculate the probability, the way you would, and so the way that given a new email, a test email, you would calculate this probability is by, plugging these parameters that you estimate from data into this formula. Okay. And then I wrote down, right, and then the other set of parameters is this, right, kind of just with y equals 1 instead of y equals 0. And then for the maximum likelihood estimate of parameters, I'll just write out one of them. Your estimate of the chance of a given word is really any word in any position being word k. What's the chance of some word in a non-spam email being the word drugs, let's say? The chance of that is equal to I find that, well, this indicator function notation looks complex. I'll just say in a second what this actually means. So the denominator, so this basically means, so if you figure out what the English meaning of this complicated formula is, this basically says, look at all the words in all of your non-spam emails, all the emails with y equals 0, and look at all of the words in all of the emails, and so of all of those words, what fraction of those words is the word drugs? And that's your estimate of the chance of the word drugs appearing in a non-spam email in some position in that email, right? And so in math, the denominator is sum over your training set, indicator is not spam, times the number of words in that email. So the denominator ends up being the total number of words in all of your non-spam emails in your training set. And the numerator is sum over your training set, sum from I equals 1 through m, indicator y equals 0. So count up only the things for non-spam email. And for the non-spam email, j equals 1 through ni, go over the words in that email and see how many words are that word k, right? And so if in your training set you have 100,000 words in your non-spam emails, and 200 of them are the word drugs that occurs 200 times, then this ratio would be 200 over 100,000. Okay. Oh, and then lastly, to implement Laplace smoothing with this, you would add 1 to the numerator as usual, and then let's see. Actually, what would you add to the denominator? But what is k? Not k, right? K is a variable, so k indexes into the words. What would you add? 10,000, cool. How come? Why 10,000? Yeah, cool. Yeah, right. Cool. Yep. Yeah. Right. Oh, I think I just realized why you said k. I think overloaded notation. When defining Laplace smoothing, I think I used k as the number of possible outcomes. Yeah, but here k is an index. Yeah, right. So, so you add 1 to the numerator and add the number of possible outcomes to the denominator, which in this case was there 10,000. So, so this is the probability of x being equal to the value of k, where k ranges from 1 to 10,000. If you have a dictionary size, if you have a list of 10,000 words you're modeling. And so the number of possible values for x is 10,000, so you add 10,000 to the denominator. Make sense? Okay, cool. Yeah, question? Oh, what do you do with words that aren't in a dictionary? So there are two approaches to that. One is just throw it away, just ignore it, disregard it. That's one. A second approach is to take the rare words and map them to a special token, which traditionally is denoted UNK for unknown word. So if in your training set you decide to take just the top 10,000 words into your dictionary, then everything that's not in the top 10,000 words you can map to a unknown word token, or the unknown word special symbol. Yeah.
How do you write the 1 before the curly bracket? Just wondering.
Oh, why did I write the run before? Oh, this is an indicator function notation. So indicator function, boy. So so this notation, right, means well. So indicator of 2 equals 1 plus 1. This is true, and indicator of 3 equals 5 is 0, is false. So that's the cool. Yes. But this is a little formula that's either true or false depending on whether yi is 0. I guess if yi is 0 or 1, this is the same as not yi, I guess, or 1 minus yi will be the same thing. Yeah, cool. Okay, great. All right. So I think both event models, including the details of maximal likelihood estimates, are written out in more detail in the lecture notes. So, when would you use the naive Bayes algorithm? It turns out naive Bayes algorithm is actually not very competitive with other learning algorithms. So for most problems, you find that logistic regression will work better in terms of delivering a higher accuracy than naive Bayes. But the advantages of naive Bayes is first, it's computationally very efficient, and second, is relatively quick to implement, right? And also doesn't require an iterative gradient descent thing, and the number of lines of code needed to implement naive Bayes is relatively small. So if you are facing a problem where your goal is to implement something quick and dirty, then naive Bayes is maybe a reasonable choice. And I think as you work on your class projects, I think some of you, probably a minority, will try to invent a new machine learning algorithm and write a research paper. And I think, inventing new machine learning algorithms is a great thing to do. It helps a lot of people on a lot of different applications, so that's one. The majority of class projects in CS229 will try to apply a learning algorithm to a project that you care about, right? Apply it to a research project you're working on somewhere at Stanford, or apply it to a fun application you want to build, or apply it to a business application for some of you taking this on SCPD, taking this remotely. And if your goal is not to invent a brand new learning algorithm, but to take existing algorithms and apply them, then rule of thumb I suggest to you is when you get started on a machine learning project, start by implementing something quick and dirty. Instead of implementing the most complicated possible learning algorithm, start by implementing something quickly and train the algorithm, look at how it performs, and then use that to debug the algorithm and keep iterating on that. Right? So I think, this is Stanford, so we're very good at coming up with very, very complicated algorithms. But if your goal is to make something work for an application rather than invent a new learning algorithm and publish a paper on a new technical contribution. If your main goal is you're working on an application on understanding news better, or improving the environment, or estimating prices, or whatever, and your primary objective is just make an algorithm work, then rather than building a very complicated algorithm at the outset, I would recommend implementing something quickly so that you can then better understand how it's performing, and then do error analysis, which I'll talk about later, and use that to drive your development. One analogy I sometimes make is that if you are, let's see, so if you're writing a new computer program with 10,000 lines of code, right? One approach is to write all 10,000 lines of code first, and then to try compiling it for the first time. Right, and that's clearly a bad idea, right? And so, you should write small modules, run it, test it, unit testing, and then build up the program incrementally, rather than write 10,000 lines of code and then start to see what syntax errors you're getting for the first time. And I think it's similar for machine learning. Instead of building a very complicated algorithm from the get-go, you build a simpler algorithm, test it, and then see what is doing well and see what's doing wrong to improve from there. You often end up getting to a better performing algorithm faster. So here's one example. This is actually something I used to work on. I actually started a conference on email and anti-spam. I was doing work on spam classification many years ago. And it turns out that when you're starting on a new application problem, it's hard to know what's the hardest part of the problem. Right? So if you want to build an anti-spam classifier, there are lots of things you could work on. For example, spammers will deliberately misspell words. A lot of mortgage spam, right? Refinance your mortgage or whatever. But instead of writing the word mortgage, spammers will write M0 RT GAGE, right? Or instead of GAGE, maybe a // right? But all of us as people have no trouble reading this as the word mortgage, but this would trip up a spam filter. This might map the word to an unknown word that we talked about just now if it hasn't seen this before, and thus allowing this word to slip by the spam filter. So that's one idea for improving spam. Actually, one of the PhD students, Hong Wak Lee, actually wrote a paper mapping this back to words like that, so the spam filter can see the words the way that humans see them, right? So that's one idea. Another idea might be a lot of spam email spoofs email headers. You know, spammers often try to hide where the email truly came from by spoofing the email header, the email address on information. And another thing you might do is try to fetch the URLs that are referred to in the email and then analyze the web pages that you get to, right? But a lot of things that you could do to improve a spam filter. And any one of these topics could easily be 3 months or 6 months of research. But when you're building, say, a new spam filter for the first time, how do you actually know which of these is the best investment of your time? So my advice to those who work on projects, if your primary goal is to just get this thing to work, is to not somewhat arbitrarily dive in and spend 6 months on improving this, or spend 6 months on trying to analyze email headers, but to instead implement a more basic algorithm, almost implement something quick and dirty. And then look at the examples that your learning algorithm is still misclassifying. And if you find that if after you've implemented a quick and dirty algorithm, you find that your anti-spam algorithm is misclassifying a lot of examples with these deliberately misspelled words, it's only then that you have more evidence that it's worth spending a bunch of time solving the misspelled words, the deliberately misspelled words problem, right? But you implement spam filter and you see that it's not misclassifying a lot of examples of these misspelled words, then I would say don't bother, go work on something else instead, or at least treat that as a lower priority. Okay. So one of the uses of GDA, Gaussian discriminant analysis, as well as naive Bayes, is that they're not going to be the most accurate algorithms. If you want the highest classification accuracy, there are other algorithms like logistic regression or SVMs, which talk about next, or neural networks, which we'll talk about later, which will almost always give you higher classification accuracy than these algorithms. But the advantage of Gaussian discriminant analysis and naive Bayes is that they are very quick to train, right? It's non-iterative. This is just counting, and GDA is just computing means and covariances, right? So it's very computation efficient, and also they are simple to implement. So it can help you implement that quick and dirty thing that helps you get going more quickly. And so I think for your project as well, I would advise most of you to, as you start work on your project, I would advise most of you to don't spend weeks designing exactly what you're going to do if you have an if you have an applied project, but instead get a data set and apply something simple. Start with logistic regression, not a neural network, or not something more complicated, or start with naive Bayes and then see how that performs, and then go from there. Okay. All right. So that's it for naive Bayes and generative learning algorithms. The next thing I want to do is move on to a different type of classifier, which is a support vector machine. Let me just check if there are any questions about this before I move on. Yeah. Oh, wait. Oh, sorry. Oh, can you use logistic regression with
Discrete variables.
Oh, I see. Yeah, right. Yes. So yes, right. So one of the weaknesses of the naive Bayes algorithm is that it treats all the words as completely, separate from each other, right? And so, right, the words 1 and 2 are quite similar, and the words, like mother and father are quite similar. And so, but with this feature vector representation, it doesn't know the relation between these words. So in machine learning, there are other ways of representing words. There's a technique called word embeddings. In which you choose a feature representation that encodes the fact that the words 1 and 2 are quite similar to each other. The words mother and father are quite similar to each other. The words whatever, London and Tokyo are quite similar to each other because they're both city names. And so this is a technique that I was not planning to teach here, but that is taught in CS230, so in neural networks. Right? But you can also read up on word embeddings or look at some of the videos or resources from CS230 if you want to learn about that. So the word embeddings technique, this is a technique from neural networks really, will reduce the number of training examples you need to learn a good text classifier because it comes in with more knowledge baked in. Right. Cool. Anything else? Cool. By the way, I do this in the other classes too. In some of the other classes, somebody get a question, I go, no, we don't do that. We just cover that in the CS229. So. Actually, CS224N, I think, also covers this. Yeah, the NLP class. Yeah, pretty sure. Yeah, actually, I'm sure they do. Okay, so support vector machines, SVMs. Let's say you have a classification problem. Right, where the data set looks like this. And so you want an algorithm to find, like a nonlinear decision boundary, right? So the support vector machine will be an algorithm to help us find potentially very, very nonlinear decision boundaries like this. Now, one way to build a classifier like this would be to use logistic regression. But if this is x1, this is x2, right? So logistic regression will fit a straight line to data. A Gaussian discrete analysis will end up with a straight line decision boundary. So one way to apply logistic regression like this would be to take your feature vector x1, x2, and map it to a high dimensional feature vector with x1, x2, x1 squared, x2 squared, x1, x2, maybe x1 cubed, x2 cubed, and so on, and have a new feature vector, which we will call phi of x, that has these higher dimensional features. Right? Now, it turns out if you do this and then apply logistic regression to this augmented feature vector, then logistic regression can learn nonlinear decision boundaries. With this set of features, logistic regression can actually learn the decision boundary that's the shape of an ellipse. Right? But manually choosing these features is a little bit of a pain, right? I don't know what I actually don't know what type of set of features could get you a decision boundary like that, right? Rather than just an ellipse, a more complex decision boundary. And what we will see with support vector machines is that we will be able to derive an algorithm that can take, say, input features x1 and x2, map them to a much higher dimensional set of features, and then apply a linear classifier in a way similar to logistic regression, but different in details, that allows you to learn very nonlinear decision boundaries. Okay? And I think, a support vector machine, one of the reasons support vector machines are used today is a relatively turnkey algorithm. And what I mean by that is it doesn't have too many parameters to fiddle with. Even for logistic regression or for linear regression, you might have to tune the gradient descent parameter, tune the learning rate alpha, and that's just another thing to fiddle with. Right? Try a few values and hope you didn't mess up how you set that value. Support vector machine today has the very robust, very mature software packages that you can just download to train the support vector machine on a problem, and you just run it, and the algorithm will kind of converge without you having to worry too much about the details. So I think on the grand scheme of things today, I would say support vector machines are not as effective as neural networks for many problems, but one great property of support vector machines is turnkey. You kind of just turn the key and it works, and there isn't as many parameters like the learning rate and other things that you have to fiddle with. Okay. So the roadmap is we're going to develop the following set of ideas. We'll talk about the optimal margin classifier today, and we'll start with the separable case. And what that means is going to start off with data sets that we assume look like this and that are linearly separable. Right? And so the optimal margin classifier is the basic building block of a support vector machine. And we'll first derive an algorithm. They'll have some similarities to logistic regression, but allows us to scale in important ways that to find a linear classifier for training sets like this that we assume for now can be linearly separated. So we'll do that today. And then what you see on Wednesday is, next Monday. What you see next Monday is an idea called kernels. And the kernel idea is one of the most powerful ideas in machine learning, is how do you take a feature vector x, maybe this is R2, right, and map it to a much higher dimensional set of features. In our example there, that was R5, right? And then train an algorithm on this higher dimensional set of features. And the cool thing about kernels is that this high dimensional set of features may not be R5, it might be R100,000, or it might even be R infinite. And so with the kernel formulation, we're going to take the original set of features that you were given for the houses you're trying to sell, or for the medical conditions you're trying to predict, and map this two-dimensional feature vector space into maybe an infinite dimensional set of features. And what this does is it relieves us from a lot of the burden of manually picking features, right? Like, do you want to have square root of x1, or maybe x1, x2 to the power of 2/3? So you just don't have to fiddle with these features too much, because the kernels will allow you to choose an infinitely large set of features, okay? And then finally, we'll talk about the inseparable case. So we're going to do this today, and then this next Monday. Okay. So, and by the way, the machine learning world has become a little bit funny. I think if you read, in the news, the media talks a lot about machine learning, and the media just talks about neural networks all the time, right? And you hear about neural networks and deep learning a little bit later in this class. But if you look at what actually happens in practice in machine learning, the set of algorithms actually used in practice is actually much wider than neural networks and deep learning. So we do not live in a neural networks only world. We actually use many, many tools in machine learning. It's just that deep learning attracts the attention of the media in some way that's quite disproportionate to what I find useful. Neural networks, I love them, but they're not the only thing in the world. And so, and again, late last night, I was talking to an engineer about factor analysis, which you learn about later in CS229, right? It's an unsupervised learning algorithm, and there's an application that one of my teams is working on in manufacturing, where we're going to use factor analysis or something very similar to it, which is totally not a neural network technique, right? But so there are all these other techniques that, including support vector machines and naive Bayes, I think do get used and are important. All right, so let's start developing the optimal margin classifier. So first, let me define the functional margin, which is informally, the functional margin of a classifier is how confidently and accurately do you classify an example. So here's what I mean. We're going to go to binary classification, and we're going to use logistic regression, right? So let's start by motivating this with logistic regression. So this is a logistic classifier, h of theta equals the logistic function applied to theta transpose x. And so if you turn this into a binary classification, if you have this algorithm predict not a probability, but predict 0 or 1, then what this classifier will do is predict 1 if theta transpose x is greater than 0, right? And predict 0 otherwise, okay? Because theta transpose x is greater than 0, this means that g of theta transpose x is greater than 0.5. Right? And you can have greater than or greater than or equal to. It doesn't matter, I guess. If exactly 0.5, it doesn't really matter what you do. And so you predict 1 if theta transpose x is greater than or equal to 0, meaning that the output probability, the estimated probability of the class being 1 is greater than 50-50, and so you predict 1. And if theta transpose x is less than 0, then you predict that this class is 0. Okay? So this is what will happen if you have logistic regression output 1 or 0 rather than output a probability. Right? So in other words, this means that if yi is equal to 1, right, then hope, or we want, that theta transpose xi is much greater than 0. This double greater than sign, it means much greater, right? Because if the true label is 1, then if the algorithm is doing well, hopefully theta transpose x, right, will be fast to the right, so the output probability is very, very close to 1. And if indeed theta transpose x is much greater than 0, then g of theta transpose x will be very close to 1, which means that it's giving a very good, very accurate prediction, very correct and confident prediction, right, that the label is 1. And if yi is equal to 0, then what we want, or what we hope, is that theta transpose xi is much less than 0, right? Because if this is true, then the algorithm is doing very well on this example. Okay. So, so the functional margin, which we'll define in a second, captures this idea that if it classifies a large functional margin, it means that these two statements are true, right? Okay. To look ahead a little bit, there's a different thing we'll define in a second, which is called the geometric margin, and that's the following. And for now, let's assume the data is linearly separable. Right? So let's say that's the data set. Now, that seems like a pretty good decision boundary for separating the positive and negative examples. That's another decision boundary in red that also separates the positive and negative examples, but somehow the green line looks much better than the red line. Okay. So why is that? Well, the red line comes really close to a few of the training examples, whereas the green line, has a much bigger separation, right? Just as a much bigger distance from the positive and negative examples. So even though the red line and the green line both, perfectly separate the positive and negative examples, the green line has a much bigger separation, which is called the geometric margin. But there's a much bigger geometric margin, meaning a physical separation from the training examples, even as it separates them. Okay? And so what I'd like to do in the next several, next 20 minutes is formalize definite functional margin, formalize definition of geometric margin, and it will pose the optimal margin classifier, which is basically an algorithm that tries to maximize the geometric margin. So what the rudimentary SVM does, what SVM in low dimensional spaces will do, also called the optimal margin classifier, is pose an optimization problem to try to find the green line to classify these examples. Okay. So now, in order to develop SVMs, I'm going to change the notation a little bit again. Because these algorithms have different properties, using slightly different notation to describe them, makes some of the math a little bit easier. So when developing SVMs, we're going to use -1 and +1 to denote the clause labels. And we're going to have each output So rather than having a hypothesis output a probability like you saw in logistic regression, the support vector machine will output either -1 or +1. And so G of Z becomes -1 or 1. So output 1 if Z is greater than or equal to 0, and -1 otherwise. Okay? So instead of a smooth transition from 0 to 1, we have a hard transition, an abrupt transition from -1 to +1. And finally, where previously we had, for logistic regression, right, where this was Rn plus 1 with x0 equals 1. For the SVM, we will have h of, I'll just write this out. Okay. So for the SVM, the parameters of the SVM will be the parameters W and B, and the hypothesis applied to X will be G of this, and we're dropping the x0 equals 1 constraint. So separate out W and B as follows. So this is the standard notation used to develop support vector machines. And one way to think about this is if the parameters are, theta 0, theta 1, theta 2, theta 3, then this is the new B, and this is the new W. Okay? So you just separate out the theta 0, which was previously multiplying into x0. Right. And so, And so this term here becomes sum from I equals 1 through n of Wi xi plus b, right? Since we've gotten rid of x0. All right. So let me formalize the definition of a functional margin. So, so the parameters W and B define the linear classifier, right? So, with the formulas you just wrote down, the parameters W and B defines it really defines a hyperplane, but defines a line, or in high dimensions, it'd be a plane or a hyperplane, but defines a straight line, separating out the positive and negative examples. And so we're going to say the functional margin of the, hyperplane So the functional margin of a hyperplane defined by this, with respect to one training example, we're going to write as this. And hyperplane just means straight line, right, but in high dimension. So this is a linear classifier, so it's just functional margin of this classifier with respect to one training example, we're going to define as this. And so if you compare this with the equations we had up there, if y equals 1, we hope for that. If y equals 0, we hope for that. So really what we hope for is for are classified to achieve a large functional margin, right? And so, so if yi equals 1, then what we want, or what we hope for, is that W transpose xi plus b is much greater than 0. And if the label is equal to -1, then we want, or we hope, that this is much smaller than 0. And if you kind of combine these two statements, if you take yi, right, and multiply it with that, then these two statements together is basically saying that you hope that gamma hat I is much greater than 0, right? Because yi now is +1 or -1, and so if y is equal to 1, you want this to be very, very large. If yi is -1, you want this to be a very, very large negative number. And so either way, it's just saying that you hope this will be very large. Okay? So we just hope that. Okay? And as an aside, one property of this as well is that so long as gamma hat I is greater than 0, that means the algorithm right, is equal to yi. So long as the functional margin, so long as this gamma hat I is greater than 0, it means that either this is bigger than 0 or this is less than 0, depending on the sign of the label. And it means that the algorithm gets this one example correct at least, right? And if much greater than 0, then it means, so if it's greater than 0, it means in the logistic regression case, it means that the prediction is at least a little bit above 0.5, a little bit below 0.5 probability, so that at least gets it right. And if it's much greater than 0, much less than 0, then that means it's, the probability output in the logistic regression case is very close to 1 or very close to 0. So, one other definition. I'm going to define the functional margin with respect to the training set to be gamma hat equals min over I of gamma hat I, where here I equals ranges over your training examples. Okay? So this is a worst case notion, but so this definition of a functional margin, on the left we define functional margin with respect to a single training example, which is how well are you doing on that one training example. And we'll define the functional margin with respect to the entire training set as how well are you doing on the worst example in your training set. Okay? This is a little bit of a brittle notion, and for today, we're assuming that the training set is linearly separable. So we're going to assume that the training set, looks like this. And that you can separate it with a straight line, but we'll relax this later. But because we're assuming, just for today, that the training set is linearly separable, we'll use this kind of worst case notion and define the functional margin to be the functional margin of the worst training example. Okay. Now, one thing about the definition of the functional margin is it's actually really easy to cheat and increase the functional margin, right? And one thing you can do, if you look at this formula, is if you take W, and multiply it by 2, and take B and multiply it by 2, then everything here just multiplies by 2, and you've doubled the functional margin, right? But you haven't actually changed anything meaningful. Okay, so one way to cheat on the functional margin is just by scaling the parameters by 2, or instead of 2, maybe you can multiply all your parameters by 10, and then you've actually increased the functional margin of your training example as 10x. But this doesn't actually change the decision boundary, right? It doesn't actually change any classification, just to multiply all of your parameters by a factor of 10. So one thing you could do is replace. One thing you could do would be to normalize the length of your parameters. So for example, hypothetically, you could impose a constraint that norm of W is equal to 1. Or another way to do that would be to take W and B and replace it with W over norm of B and replace B with, right, just divide your parameters through by the magnitude, by the Euclidean length of the parameter vector W, and this doesn't change any classification, it's just rescaling the parameters. But it prevents, this way of cheating on the functional margin, okay? And in fact, more generally, you could actually scale W and B by any other value you want, and it doesn't matter, right? You could choose to replace this by W over 17 and B over 17, or any other number really, right? And the classification stayed the same. Okay? So we'll come back and use this property in a little bit. All right, so to define the functional margin, let's define the geometric margin. And you'll see in a second how the geometric and the functional margin relate to each other. So let's define the geometric margin with respect to a single example, which is, so let's see, let's say you have a classifier, right? So given parameters W and B, that defines a linear classifier. And the equation Wx plus B equals 0 defines the equation of a straight line. So the axes here are x1 and x2. And in half of this plane, in this half of the plane, you have W transpose x plus B is greater than 0. And in this half, you'd have W transpose x plus B is less than 0. And in between is the straight line given by this equation, Ws transpose x plus B equals 0. Right? And so given parameters W and B, the upper right is where your classifier will predict y equals 1, and the lower left is where it will predict y is equal to negative 1. Okay? Now, let's say you have one training example here. Right? So that's the training example xi comma yi. And let's say it's a positive example. Okay? And so your classifier is classifying this example correctly, right? Because in the upper right half plane, in this half plane, W transpose x plus B is greater than 0, and so in this upper right region, your classifier is predicting plus 1, right? Whereas in this lower half region, it'd be predicting h of x equals negative 1. And that's why this straight line, where it switches from predicting negative to positive, is the decision boundary. So what we're going to do is define this distance to be the geometric margin of this training example. It's the Euclidean distance is what we'll define to be the geometric margin. So let me just write down what that is. So the geometric margin of, the classifier of the hyperplane defined by WB with respect to one example, xi, yi, this is going to be gamma I equals W transpose x plus B over the norm of W. And let's see, I'm not proving why this is the case. The proof is given in the lecture notes, but the lecture notes shows why this is the right formula for measuring the Euclidean distance that I just drew in the picture up there. Okay? And I'm not proving this here, but the proof is given in the lecture notes. But this turns out to be the way you compute the Euclidean distance between that example and the decision boundary. Okay? And this is for the positive example, I guess. More generally, going to define the geometric margin to be equal to this, and this definition applies to positive examples and to negative examples. Okay. And so the relationship between the geometric margin and the functional margin is that the geometric margin is equal to the functional margin divided by the norm of W. Finally, the geometric margin with respect to the training set is, we're again use this worst case notion of look through all your training examples and pick the worst possible training example, and that is your geometric margin on the training set. Oh, and so I hope the notation is clear, right? So gamma hat was the functional margin, and gamma is a geometric margin. Okay, and so what the optimal margin classifier does is choose the parameters W and B to maximize the geometric margin. Okay. So in other words, the optimal margin classifier is basically the baby SVM. You know, it's like a SVM for linearly separable data, at least for today. And so the optimal margin classifier would choose that straight line because that straight line maximizes the distance or maximizes the geometric margin to all of these examples. Okay. Now, how you pose this mathematically, there are a few steps of this derivation that I don't want to do, but I'll just describe the beginning step and the last step and leave the in-between steps to the lecture notes. But it turns out that one way to pose this problem is to maximize gamma W and B of gamma. So you want to maximize the geometric margin subject to that every training example must have geometric margin greater than or equal to gamma, right? So you want gamma to be as big as possible, subject to that every single training example must have at least that geometric margin. This causes you to maximize the worst case geometric margin. And it turns out this is not, in this form, this isn't a convex optimization problem, so it's difficult to solve this with algorithm like gradient descent, initial, there are no local optima, and so on. But it turns out that via a few steps of rewriting, you can reformulate this problem as into an equivalent problem, which is to minimize the norm of W subject to the geometric margin. And so it turns out, so I hope this problem makes sense, right? So this problem is just, solve for W and B to make sure that every example has geometric margin greater than or equal to gamma, and you want gamma to be as big as possible. So this is a way to formulate an optimization problem that says maximize the geometric margin. And what we show in the lecture notes is that through a few steps, you can rewrite this optimization problem into the following equivalent form, which is to try to minimize the norm of W subject to this. And maybe one piece of intuition to take away is, the smaller W is, the bigger, right, the less of a normalization division effect you have, right? But the details are given in the lecture notes, okay? But this turns out to be a convex optimization problem, and if you optimize this, then you will have the optimal margin classifier, and they're very good numerical optimization packages to solve this optimization problem. And if you give this a data set, then, assuming your data is separable, and we'll fix that assumption when we reconvene next week, then you have the optimal margin classifier, which is really the baby SVM. And we add kernels to it, then you have the full complexity of the SVM algorithm. Okay? All right, let's break for today. See you guys next Monday.